I will talk today about characterizations of input to output stability for infinite dimensional systems. And this talk today is based on a paper that was recently conditionally accepted at Transactions. And this is a joint work with Sergei Dashkovsky and Andriy. And yeah, I'm very happy to present this today. Okay, let's maybe start with a bit of definitions, and then we can talk a bit more sophisticated about the motivation. So what kind of control system do we want to deal? So we consider a very abstract kind of control system, I would say. So we have a time set, which is the non-negative real numbers. In the paper version, we also considered the natural numbers. So it's also possible to modify here a bit, but for easiness of notation, let's stay with the real numbers. The state space is X, the input value space is U, and we consider the input space, calligraphic U, which is some linear subspace of the mappings from the time domain to U. We have certain restrictions on this time domain, but let's say that, for example, the Lebesgue spaces are included in this. So I would not like to go into more detail to not make it more complex at the moment. Furthermore, we have a transition map phi, which is a map from the time domain and the initial state X and the input space to X. Okay, and we want these control systems to satisfy the following conditions, namely the identity property, causality, and the co-cycle property. These are very standard restrictions which we usually have for many kinds of systems, for example, ODE systems, PDE systems, time delay systems, but also like discrete maps fulfill these conditions. Okay, and for this control system, we now define an output. This is something that is also very common, but not in nonlinear stability theory, where usually ISS is treated. And we generalize ISS by allowing now output maps. Okay. What is added here, you see that now we have an output value space and an output map. So we have some normed vector space and a map from the state space times the input values to the output map. And we will, in the following, denote this output values or this output function to be more precise by y. Yeah, so you can consider it just as an input-output system where u is the input, y is the output, and something happens in between, which is nonlinear in this case. Okay, yeah, very short a trip to the comparison functions. I wanted to reduce this. We have the k-infinity functions, which are non-negative real functions from the non-negative real values to the non-negative real values, continuous. And in the case of k-infinity functions, they should be strictly increasing and unbounded, and it should map 0 to 0. And the second comparison function we want to introduce has two components. So from the non-negative real values squared to the non-negative real values. And in the first component, we have a strictly increasing map starting at 0. And in the second component, for each fixed first component, we have a strictly decreasing mapping to 0. So strictly decreasing to 0. Okay, now we can formally define the input to output stability. You may, as you are all experienced in input to state stability, this might look familiar to you. So the difference to input to state stability is that on the left-hand side, we now have the output. So what do? We map or we bound the output value pointwise by a KL function of the initial state and time. And we allow some perturbation, which is in the size of this gain norm of u. Yeah. So what does this mean intuitively? We have here. Let's first consider the case where we have 0 input, and then we have here some bound, which is in terms of the initial condition, yeah, and it is falling along the trajectory, and the output should remain below this red dashed bound. Now in the second picture, we have a non-zero input, and this basically means that this is too much to ask. We have no convergence, no uniform convergence to 0, but we converge to some bounded set around 0. And the trajectory remains then, or the output trajectory remains below this shifted red dashed line. Okay, and input to output stability generalizes the input to state stability. There is already a theory for finite dimensional systems, which was introduced in the 2000s years. So finite dimensional IOS theory is already includes for ODE systems superposition theorems. There's a Lyapunov theory, and there's also a small gain theory for finite networks. There are applications in very many fields, also because it's maybe a bit more intuitive from a application perspective than ISS, because when do we consider infinite dimensional systems where we know the whole space, the whole state of a system? So, for example, multi-agent systems, coverage controllers, neural networks. These are areas where iOS is considered. Yeah, as I said, a special case is the infinite dimensional ISS theory, or is ISS theory, because then the output map is just the identity, and the output itself is also just the state space. And for this special case, there is also a theory which is quite well established, which was given by Andri and Fabian Wirth one time here in the characterizations of input to state stability for infinite dimensional systems. And for general input to state stability theory, I want to refer to this survey written by Andri and Christophe Brieux. which is also very helpful to get an idea of the state of the art. Yeah, but for input-output systems, there is much less known. And the difficulty already for input-to-state stability was that the methods are partially not transferable to infinite dimensional dimensions, because we have certain problems with uniformity of several properties. So when in finite dimensional spaces, the continuity or Lipschitz continuity of the output map is providing several properties. This is not the case. So, for example, for bounded initial conditions and input, we do not automatically have or several uniformity properties do not transfer for non-compact spaces. And a second problem is also that the forward completeness and the bounded reachability sets, which we have in finite dimension, does not transfer. And these problems also consist in input-output systems. And therefore, we wanted to introduce an iOS theory. And especially we started with iOS characterizations, iOS superposition theorems for infinite dimensional systems. So what do superposition theorems mean? This basically is that we want to have equivalent properties of which are equivalent to iOS, but are somehow weaker. So we want to express iOS in terms of stability and attractivity properties. Yeah, so the nonlinear control theory really lacks this iOS theory yet, because this is very crucial when we want to consider Lyapunov theory or small game theorems. Then it's inevitable to first have an understanding of iOS characterizations and superpositions. And also, we expect that this work will have an effect on Lyapunov-Krasovsky theory for time delay systems. Okay. Yeah, a big part of this work consists of finding the right definitions. This is, in fact, a very complicated point, and yeah, unfortunately, we will have to manage a lot of definitions today. But I promise this is the worst slide that you will see. So yeah. This in this first definition slide, we consider regularity of systems with outputs, and what we have here at first is the so-called output continuity at the equilibrium point, which basically means that for a fixed, for a fixed time tau, which is arbitrary but fixed, and for some small parameter epsilon, we are able to choose a parameter delta small enough so that for initial values, small initial values and small inputs, we remain in this finite time in a tube which has output smaller than epsilon. The next property is bounded output reachability sets, which basically means that when we choose bounded inputs and we choose a bounded initial state, then in finite time we will stay bounded, but uniformly bounded. So we remain for all possible outputs, we will remain finite. Okay, and the second one is this two last properties. They are directly referring to the output map H. So this is maybe a bit easier to understand. So we say that the output map H is bounded on bounded sets if this map H can be bounded by a function that is growing in the initial state and is growing in the input and some constant C. And we even say that it's k-bounded. This is stronger because it just means that this parameter C is 0, which basically means that we have some bounded on bounded balls condition that says when input and initial state are 0, then also the output must be 0. Okay, so much about the regularity of systems. And now we consider, in fact, stability properties. So there are several stability properties, but for what we want to do, it's very important that we have a uniformity in the output, which means that we can, for bounded input and bounded state, the output gets uniformly bounded. Yeah, and even more, when input and initial state get small, then also the output gets small for all times, or remains small for all times. That's maybe the better formulation. And the next property looks quite similar, but there is a difference. Output-Lagrange stability means that we bound also the output in terms here of the initial output. So this is a bit different. I will explain this later in an example. Because like also when the initial state might be very large, then the output might still be a small value. And this means that these definitions are distinct from each other. However, when we look at the ISS case, so when the state and the output are equal here, then these two definitions they are equivalent. Yeah, and also this makes a much more complexity for output systems compared to full state systems. Okay, next we look at attractivity, and for attractivity, let us first introduce this output uniform asymptotic gain property, or UHG, which means that, well, this attractivity is also uniform for bounded initial states. So we have here some time tau, and for bounded x and bounded u, we will have a fixed epsilon that we come into a neighborhood of this gain radius gamma of norm u. Yeah. So what does this mean? Let's have a look at the picture. So we have a gamma of a norm u, which is the lowest of these lines here, and basically what will happen is that we will come very closely to a neighborhood of this gamma of norm u. Here it's even stronger. Here we will end up inside of this set, but generally speaking, we will only get into an epsilon neighborhood, and we will remain from then on in this neighborhood after some time. Opposed to that, we also have, sorry, I forgot about this slide. Yeah, we have further notions of, this should be, it's just attractivity, not weak attractivity. Namely, OHE, output asymptotic gain property, and the output global uniform asymptotic gain property, which are variations of this definition here. In the first case, this Tor is just independent of or is not uniform in R and S, but it depends on X and U itself. So we are missing the uniformity. And in the second case, it should be globally uniform, which means that it does not depend on S. And in fact, this makes a difference. However, we have the following relation. So this the stronger property OG implies OUHE, and also the backwards direction is true as long as the system has bounded output reachability sets. But there's a difference between OUHE and the non-uniform version, because which is already known for finite dimensional systems, that this equivalence does not hold. However, in finite dimensional ODE systems, we will always have the equivalence between the first two systems, also because when we treat ODEs, then this BORS property always holds true. Okay. Now, sorry. Now the next property is weak attractivity. The formal name is output uniform limit property, and weak attractivity is the right notion in this sense, because what we have is that we get into each epsilon neighborhood of this perturbance radius gamma of norm u, but we don't need the system to remain inside. So you can see here that afterwards it will leave this epsilon ball again. And so this is basically the difference between the weak attractivity and the strong attractivity. That after each, reaching each neighborhood, the system again can leave this neighborhood again. And in fact, the same consideration that we already had for OUHE, we already have it. We also have it here. So we can modify this notion in terms of not considering uniform initial state and input convergence or attractivity, but for each initial state and input individually. And also we can consider a global uniform limit property, which then states that this time that we reach the radius is independent of the input. And this picture here looks a bit different from the one for OUHE, because here we only need that H is a bounded operator. So basically that it maps bounded sets on bounded sets, as we said before. And then the global version of GU lim is equivalent to OU lim. But also for the non-uniform version, this is in general not equivalent. This O-lim property is weaker than OU lim. However, for finite dimensional ODE systems, these three definitions are all equivalent. And this also is a major challenge when we want to deal with the infinite dimensional case. Okay. And now you made it. We have all the definitions behind us, and we come to the main result of our research. And let me maybe start in the middle because of this figure, where we characterize iOS. So iOS is indeed an equivalent to a common strong attractivity OUHE. Then the OCEP property was output continuity at the equilibrium point and bounded output reachability sets. This is the weakest notion that we found, and the strongest equivalent notion, so to say, is that it's also equivalent to the strong attractivity property and output uniform global stability. Yeah. What is maybe surprising is that in none of these notions we have the OU-lim property, which I just introduced, and this is because it's just not we did not find an equivalence on that, or let's put it differently, that there is no such characterization, because even when we take OUGS and instead of OUHE, we put the weaker OU-lim property, then we can show, and I will show the example later, that these properties are not equivalent to iOS anymore. Yeah, this when we exchange the weak attractivity property for the attractivity property, then we get something that is in fact weaker than input-output stability. On the other hand, what we can also consider, which is also quite useful, is when we not only look at iOS, but iOS combined with the output-Lagrange property. So this was the stability property on the output space. Because in this case, it is possible to characterize iOS and OL equivalently with the weak attractivity property, combined with still the stability property on the output space. And what we need furthermore is that we have a k-boundedness of the output operator, which is compared to the others not a very strong restriction. Okay, so some of this is a bit surprising, because when we look at this result from the paper from Andri and Fabian Wirth, which I mentioned already earlier, which was discussing input to state stability, then what we see here is that we can characterize ISS in terms of UHE. So you just drop the O basically, and then you get the stability properties on pure state spaces, CEP and BRS. Which is basically, let me go back, this notion here, but instead of here having to treat with the OUHE property, we can it's even enough to look at U-lim. Yeah, so this here can be weakened. So why that? The intuition behind it is that for ISS systems, the OL property is equivalent to the stability property on the state space, and then IOS already implies the OL property. But this is not true in general. And in this case, then these three layers somehow converge. Okay, but however, we were able to prove this result from 2018 as a corollary, and show it from our more general results on input-output systems. Okay. Another result that we found is input the one on ISS again. So we again found an ISS superposition theorem, and for this it's necessary to introduce another definition. So input-output to state stability. So the difference, this notion basically means that, or is a nonlinear version of detectability. So instead of bounding in iOS, we bounded the output in the terms of the initial state and the input, and here we bound the trajectory, so the state by again the initial state and the past inputs, but also in terms of the output. So what does this mean? Basically, when we put the input and the output zero, so this is the zero dynamics, then we have a zero dynamics that the state is converging to zero. But when we consider a initial this should be a U. When we consider a non-zero input and a non-zero output, then it's not possible anymore or not necessary anymore that we reach to zero, but we will converge to a radius that is bounded by the past values of the input and the output. Okay. And what can we achieve with this? So when we have a control system with outputs, then ISS can be characterized in the case that H is k-bounded by input to output stability and input-output to state stability. Yeah. So in some context, I would say that IOSS is the dual to iOS, as much as detectability is the dual for controllability. Yeah. So then iOS is more or less the controllability part, and iOS is the detectability for the nonlinear systems. A similar result for finite dimensional systems already existed before, but for infinite dimensional systems, it's crucial that H is also k-bounded. Okay, these are the main positive results, and next I would introduce a few counterexamples to make everything a bit more touchable, let's say. So in fact, iOS and OL are input to output stability, and the output-Lagrange stability was the stability completely on the output space are independent properties which can be seen in a simple one-dimensional example. We just have a converging system, but the trick is that we have an output that has a root that is non-zero. Yeah, and when we start at exactly this root, like at x0 equals pi, then the initial output will be 0. But afterwards, when the system converges, the output will first increase and then again decrease. And so the output trajectory cannot be generally bounded in terms of the initial output. Okay. Next is that, as I promised, that even the stronger weak attractivity property, output global uniform limit property, and the output uniform global stability do neither imply IOS nor OL. And for this, I have a system in polar coordinates. The system is nothing special. It's just like a rotation. And the output is the first component. And of course, then when we start, of course, this is attractive because we come regularly to the 0. Yeah. And it's of course also stable. But it's neither IOS because we have no attractivity, and it's also not output-Lagrange because like we are starting here again at 0 and afterwards it's increasing, so we cannot bound the output in terms of the initial state. Okay. Then the next property is a bit more complex. So the system that we are treating here is that basically showing that it's not very easy to provide characterizations for the output-Lagrange property. I did not provide any characterizations yet, and maybe I will also not do during this talk because we will need a lot of more definitions. The point is that these notions that we introduced are not enough to imply the output-Lagrange property. And therefore, we have to basically find new notions. The idea maybe behind it is that for output-Lagrange stability, we bound the output in terms of the initial output. And all of, even when we have a local output-Lagrange stability, this is not enough because this is a property that bounds the output in terms of the input. And also this property is a property that bounds the input in terms of the initial, bounds the output in terms of the initial state. And to look at this image here, so the radius is the independent variable. So what we have here is outside of the unit ball, we have a constant convergence, and inside, the convergence is going to 0. So inside the unit ball, what we have is exponential stability, and outside, we converge towards this set. However, what we have here is that the output, or we have a rotation, and the rotation is getting very slow when the radius is getting large. And this basically helps us then to construct an output which is going to 1. So each of these output trajectories is at some time going to 1. But at some times it was very large. And no, sorry, the rotation is anti-clockwise. And then, of course, this the output-Lagrange property is not satisfied because for each initial output, we can get an arbitrarily large output at some time. Okay. So all of these were finite dimensional examples until now. Now we look at something a bit more difficult because we want to show. So maybe I first show where we actually want to go. We want to show that the um, output uniform asymptotic gain property and the output global uniform asymptotic gain property are not equivalent. For this, let's start with an example that also was introduced in this paper by Andri and Fabian Wirth. And we modified this example a bit. Namely, we introduced this term here. So this is an infinite dimensional example. Infinite many components and in L2 space. And we also have the zero component, which should somehow encrypt time. So this is basically a non-autonomous example, but as we only treat autonomous systems here, this is somehow to be encrypted. And so this component here is basically the time then. And the other components are giving some attractivity. So what is happening here? So with each component, we are having a bit more of a singularity. So basically, when increasing the component, we are converging to a singularity at 1, and after some time, as asterisk, we are being in a attractive or locally attractive neighborhood of 0. Yes, and the difference to this example here is basically that we introduced this extra term here, which is responsible for a uniform singularity at 1. Okay. So what do we have here? We have a forward complete system, and this is why the system is looking quite complicated, because we want a singularity, but we do not want that the system is not forward complete anymore. And we have basically we only have 0 input. So we have attractiveness of the trajectory, and we have local stability, but still this does not imply that the system is having a bounded output reachability set. However, the actual reason why I'm introducing this example is that we want to shift the singularity. So let's go to the next example here. Which does not have a lot of difference. The actual difference is actually that we are slowing down the system. So the system is moving more slowly, and the singularity is then shifted to the point 1 plus norm of u square. And the sense of all this is that we cannot find anymore a global parameter or a global convergence parameter, because the singularity is shifted with larger u, and then the attractiveness is only starting later, and there's no uniform attractiveness in terms of the output. So this is the actual aim that we had, that we could show that the output uniform asymptotic gain property and the output global uniform asymptotic gain property are not equivalent anymore in infinite dimensional systems. And for finite dimensional systems, we have this equivalence. So the system is crucially infinite dimension. This example is crucially infinite dimensional. Okay. Yeah, so I'm coming to the summary of my talk. We introduced several stability and attractivity notions. Um, I know that these were quite many. I tried to stick to the very important ones, but when you want to have a look in the paper, we still characterize some more properties, which might be interesting for you when you want to work for that in that area. We gave a superposition theorem for iOS. We gave a superposition theorem also for the combined iOS and output-Lagrange stability. And we also provided a superposition theorem for input to state stability. Furthermore, we gave several counterexamples which distinguished these notions. As I said, I warmly recommend you to have a look in the paper here, where we also have more relations between other stability and attractivity properties, and we also characterized the output-Lagrange property. Yeah, as an outlook, our next research topics are iOS Lyapunov characterizations, which are also based on these results here. And we also want to introduce small gain theorems for infinite dimensional systems. And with these words, I want to thank you for your attention, and I'm open to your questions now.